polymer physics. One announcement is by the class ends, I hope everybody can drop the exam on that table, put your name down, face down. And I need every single one of you, because I haven't put the score to my grading sheet. I need to enter yours. Make sure you put it there. Okay, so now the chapter 6 is behind us. We're going to focus on chapter 7 again. It's polymer solution. We had 2 courses on this already. We discussed about 2 items. We talked about thermodynamics a little bit. Then we talked about entropy. And hope everybody still remember what entropy is and how we calculate it. So I will do a quick recapture. Then today's topic, we're going to talk about entropy of the mixing. Okay, we will discuss how heat exchange can be captured using the entropy term. And by the end of this lecture, we should be able to talk about regular solution theory and discuss how we can predict if 2 solvents will mix or not. So this is what we talked about last time when we mix in a box of solvents A, in this case white beads and red beads, how does the entropy will be calculated. We discussed about how we can put the different of them into each side of box and how we can get the number of states, which is omega's meaning. So if we get a number of different states, we should be able to calculate the entropy. And by the end of the last lecture, we reached the conclusion that in the regular solution theory, our entropy of mixing delta S mix is equal to K, Boltzmann constant, times number of moleculars times x1 plus m2 log x2. Okay? So one of the important conclusions from that mixing theory is that when you mix 2 solutions, the entropy is always favors mixing. So delta S is always going to be a negative value. And we talked a little bit about that. So entropy always favors mixing. So why in some cases you can't mix 2 solvents? Usually something that everybody can understand is when we mix cooking oil with your water. A lot of people tell you don't dump those oil in the drain for a good reason. They don't mix. It doesn't seem like we're, from entropy point, it's done fully right. So why that's the case? And we didn't talk about anything about entropy so far, or entropy so far. So today we're going to talk about entropy, and entropy will explain to you why some of the solvents will not mix. Okay? Let's begin. Before we talked about that, we need to introduce a concept called cohesive energy density. So this particular term, delta EV divided by V, defined as where delta EV is energy, heat, of vaporizing a volume of V of liquids. So imagine you are boiling your water. So how much energy turns a part of water from liquid state to gas state is what the energy we're talking about here. And we know this is taking the energy, right? Because in the liquid states, your molecules are more closely packed. There's Lennard-Jones forces, which basically intermolecular weak forces bond them together. So if you want to liberate them, let the molecule become gas, in this case, your intermolecular distance will be much bigger. In that scenario, you will have no interactions, or more or less. Or at that distance, your interaction will be negligible. Okay, so that will be the gas states. So this is the way can help us understand one important concept is how much force is holding 2 liquids molecular together. Does that make sense? If you boil, you separate something packed closer to something far away. Make sense? Yeah. If two of you hold really hand, strong hand, we need to pull you guys apart. That's the energy we need to break. There's energy of friendship, there's energy of husband and wife, all ranges between different molecules. But in this case, the importance is these two molecules have a certain energy, and not every single molecule holds the same amount of energy. Some of them are stronger, some of them are weaker. And this would be defined how much energy we can exchange. So delta EV divided by volume, because it's how much energy you need to vaporize a liquid, depends on how much liquid you need to vaporize. So we normalize by V, that will give you the energy. So what is the attraction force is mostly presented a dispersion force. So these are dipole moments. So electron moves within molecular and produce a dipole. So everybody knows what is dipole? Probably not, right? So let's explain. So when you have, let's say, carbon, CH, CH, CH. Let's put in a fluorine or chlorine on that. So your electron is not going to be uniformly distributed along the bond. Depends on the bond strength. If it's something has very polar, for example, fluorine, you will generate a slightly positive charge, a negative charge here, a slightly positive charge here. So this creates imbalance in electron clouds. It's not an equal share of wells. In this case, carbon is slightly positive, fluorine is slightly negative. So in this case, you create electrical field within a molecule. It's very small, but that's what we call a dipole. So if you have something with another molecular, you can imagine they would have interactions. This would have a sort of weak force with another fluorine. For example, hydrogen bond is another bond. In water molecular, you have H, and oxygen would form such bond. So these are not as strong as molecular bond, like carbon-hydrogen bond, but they are weaker, but they exist there, okay? So that will be one of the force could allow your molecular to have interactions between them, okay? These are the most important example. In chemical engineering or other field, people also call them Lennard-Jones force. So these are the weak force between molecules.
I've heard London dispersion forces.
Yeah, that's one of them. So these are strong bonds. These are the weak bonds. So they like each other, but they don't tell each other they like each other. So they're just thinking. It's there, but it's weak. It's very easy to separate them, okay? But if you want to break a carbon-fluorine bond, it costs a lot of energy. So that's where in polymer chemistry, when you build a break bonds, you need a catalyst to make that happen. So why that's important? Because when we talk about mixing, we're exchanging interaction between pair of molecular. In one case, think about mixing water and oil. I like to use this example. Before we mix it, you only have water interacting with water, oil interacting. When we mix them, you will have 3 interactions. There's a chance a water molecule in water oil can still see each other. Then there's water with oil, right? Then oil can interact with oil. So this can be illustrated here. Think about the molecule we draw on this lattice. We draw again a Y bead and red bead and white beads. So we can assume there's 3 types of interactions. So we can design these into, first, let's call these W. W is energy associated between a pairwise interaction. So W, 1, so this 1 denotes the interaction between the red beads. So 1 red, another 1, another red. So it's an interaction between 2 red beads. And of course, when we mix it, we would have type of second interaction called W22. So these are the interaction between the Y beads. And we mix them. You should also has possibility to generate interaction between the red beads and the white beads. That's very straightforward. So these are just defining some of the interaction. How can you get this interaction? But we sort of talked about by measuring the cohesive energy, which is, one way you can do it is by boiling it. Later we will introduce other ways to measure it. So you can imagine there is a certain interaction in the red bead, a certain interaction with white bead, and certain interactions with white and red beads. So now, when we mix in things, we can now start to use these interaction force to calculate how much interaction we have before we mix them and after we mix them. That's how we calculate delta H, or enthalpy differences. So delta H would be mixing. Enthalpy of mixing will be equals to the mixed phase. Here we call it H, solution mix. Okay? And minus H pure. Pure is what before we mix in. So in this case will be, if we have a box of red, a box of white, that will be a box of red, a box of white. This will be representing the interaction you have mixed state. Same like if we treated delta S. So it will be after the state we mix in minus what we have before we mix in, okay? So there's a few assumptions we need to make in order to use some simple assumption, similar like we talked about before. So those that make sense because we want to talk about no change of volumes, so the number of lattice is the same when we mix in. Like we did it, if we have 9 box plus 9 box, it will be 18. There's no box missing. And then the other part is the surface of each molecule is homogeneous. It doesn't matter which is, where are they contact. When it's large enough, we ignore for example, the molecule at the edge of the container that you only interact with one side. When it's big enough, you can think about everything, every single molecule is the same. So, first, it's easy to understand what is in the pure state. So in the pure state, let's do an example. If I have a pure state of, let's say, 3 by 3, let's use y dots. So imagine those are y dots. So how much interactions? If we tell you that each pair interaction is W11, so each of them will have W11. So how do we calculate how much interactions we have? It's written here. So I want everybody to take a look at how we calculate it. The enthalpy before we mixed for molecular 1 or the red bead, how we calculate. It's given us Z. Z is, remember, number of sites. If we draw a box like this planar, Z would equal to 4. That means they have 4 closest neighbor. We have a very small box, so some of them on the edge don't think about that. Z is number. M is moles of molecular, red molecular, times W11, that's interaction between one molecule to the other, and divide by 2. Okay, can someone help me explain why we can write this way?
What was M again?
M is mole of molecular, so number of molecular.
Okay.
So for example, if we have 1 mole of red beads, this will be 6 10 to the power of 23. Okay? And Z is number of sites. So why?
Because it only interacts with its next neighbor?
Yes, we only consider short range interaction like Joseph said. So for each molecular, how many closest neighbor we have? It's defined by Z. So Z times M1 is total number of pair. Could have interaction. Right? So imagine I'm one of the beads. I have 4 neighbors. So imagine this is a very big. This is infinitely big, okay? Because in real case, it's not going to be 9. So this guy has 4 neighbors. He has 4. So he could induce 4 pair interaction. This is M11 between these two, M11 between left and right. So each direction has N times Z, sorry. Z times N11 times W11. Each pair has this much interaction. We have number of this number of molecular. Each one has this closest neighbor. So if I give you an example, this would be 4 10 to the 1 mole. 1 mole would be 10 to the power of 23. That's how big a mole is. Okay? And this is just the energy, how much we had. But this is different with what we wrote here by a factor of 2. Why?
Because currently it's counting every neighbor as distinct, but they share. So
Yeah, perfect. Jonathan, good job. Because, I will count this guy has a neighbor here, and he has a neighbor of him. So this interaction is counted twice, because a pairwise interaction. So that's why we normalize by 2. Okay? A single interaction requires 2 contact points. So these are number of molecular times its neighbor, Z closest neighbor, times interaction strength between 2 red one. It's pretty much simple to calculate the second half, which basically we just have W22, right? So we need to know how many white molecular is out there, how much neighbor you have, closest neighbor. We time them and we divide by 2. That's how much total interaction. And we times each pair interaction is defined by this strength. All right. The easy part is done. So the question is, how can we get this? Do I have that? Okay, so let's stay here. This is a little bit busy slides, but let me clean up the board. Let's draw it and let's do a little bit discussion about how to get pairwise interaction for a mixed state. So this would be the simple case. Then we would have a more complex case. I wouldn't ask everybody come in to fill it. I'll pick 9 spots. 5, 6, 7, and 1 more. Okay. So this would be one way we can fill it, right? So the question is, how do we count delta H in? We need to count how many different pair interaction, right? So these, you can see we are pretty complex because we do have possibility to have circle and circle interaction. Let's just call it M11. In the mixed state, it's possible that you have 2, how do we want to call it? Let's call it red, just to be unified with the slides. So this will be the
Can we say type 1? So
okay, yeah, perfect. Type 1 interaction. You could also have type 2 interaction. And you can have type 1 mixed with 2, M12. right? You can see these two would be interacting. So now how do we count delta H after we mix there? I'll give everybody a minute to think a little bit. We have some of the pair 1, M11. So we need to count how many is M11, how many is M22, and how many is M12. Then we can get delta H. Because we just need to know 3, then we can, those are parameters we can simply add them together. Okay? Yes?
Are we assuming that it is as likely for M12 to occur as M11 or M22? So like a perfect mix, like where they are equal?
Very good question, Amy. So this is the essence of what? So mixing should be uniform, but the chances is not 50-50 for molecular. In our case, it is. I'll tell you why. Because we're mixing 9 red versus 9 blue, or 9 of one type of molecular, 9 of two. So we have an equal number of them. In the mixed states, now you can calculate what the chances of then seeing one versus the other. So if you go to a country fair, some type of, they have lotteries, so everybody played with it. Maybe you can borrow this.
Sure.
Some of them would get a bag, look like this. This is actually not a bag, it's probably a screen protector. But you can put your hands in. So now we only have 2 colors of pen. I'll put both of them in. But imagine you have 10 pens, not 2. Half of them will be the green, half of them will be black. If I ask Amy, put your hands in, pick a random one out, what the color it will be red, what the chance of it be black?
50-50 sort of.
Yes, it is 50-50 if you keep doing it. So your chance of one seeing the other, your chance of getting a red or chance of getting a black, or blue, or this is green or black, depends on how much you have in the pool. Does that make sense? If the lottery system, he only put 1 green, but he put 99 blacks, the chance of you get this is very low. So same for the mixing system, we need to think about under the concept of chances. Right now we're 50-50 because we have 9 of one molecular, 9 of type 1 and 9 of type 2, right? So if we put a mix in, think about you, imagine now you are one of those 9 molecular. Okay, you're 1 out of 9. I could be, let's say type of 1 should be, imagine this is exactly molecular we are looking at. Okay, this is a guy, and it's you. What is the chance of the neighbor to be a dot versus a cross? 50-50, right? Does that make sense? I'll give you a moment to digest. Or you think about this classroom, we have 1, 2, 3, 6 female students, if the counting is right, and 8 male students. No, not perfect balance, but close. So if the Derek calls a random number saying, I want to meet one of the students, what is the chance of him meeting a female student? 6 out of 14, right? Or we put it this way, if I ask Amy to randomly throw a number and pick a student to go out for dinner. Could be interesting if you actually do that. But what's the chances of you having a dinner with another girl?
6 out of 14.
Yes, right? 6 out of 14. What's the chance of you actually having dinner with a boy? So it's going to be 8 of 14, right? So that's a way you can think about pair interaction. In the solution mixed states, the chance of having is first we can count the number of contact, then we can count of interaction. So the chances of having a pairwise interaction with itself will be depends on how much chances you have type of 1, 1. So in this case, imagine you would have n. This is the total number of molecular times z. That's the same. Z is number of contact points. But now we need times a chance of finding it itself times W11. So that's the chance of total number of molecular M11 times the chance of meeting a Y molecular, or 1 molecular, and times the interaction. Let's only describe half of it, correct? It need to add the chance of this guy meet a molecular 2, 2. And interaction would be 1, 2. Hey, we don't look like
I do not
that.
understand this at all.
Okay, so let's explain in the context of having dinner. Can I still use you as an example? So we have. So do you understand what z times M11? So that means how many total of one type of molecular. So you can imagine these are going to be female students. Z in this case, in the scenario of going out for dinner, will be 2. Okay, 2 times 6. The chance of you finding a female student would be 6 divided by 6 plus 8. So you have 6 of 14th chance of having a dinner with a female student. So that's the interaction between female and female. Does that make sense? Or I can explain one more time. We got a lot of time to go through this.
Yeah, I get the first term now. I don't understand the second term.
So this part?
No, the one under it.
This part?
Yeah.
Under this.
Yeah.
So in the mixed states, the top part, it's counting just 1 and 1 interaction. The bottom part is counting 1 and 2 interactions. So in other words, we need to count this green versus green, and then we need to count green versus black. And we're not done yet. We need to also count black, black, and black with green. So we need to count 4 types of interaction in this mixed states. Does it make sense? Let's slow down one more time. In the mixed states, we have 1, 2 type of molecular. For any green, it can have a chance of having green-green interaction or green-black interaction. We can call it M11 and 1,2. So what we are doing is counting 1,1 and 1,2 interaction. How do we count 1,1 interaction? We need to count number of sites times total number of 1,1 molecular times the chance of seeing another 1,1 molecular. Okay? So this is the chance of seeing a 1,1 molecular in the pool of M11 plus N22. If you mix 1 mole versus 1 mole, it will be 1 divided 1 plus 1, so it's going to be 50% or 0.5. And times interaction parameter is W11. W just is pairwise interaction.
And this whole thing is equal to H for mixing or delta H?
it's H solvent. So after we mix it, and we are not done yet. It's only half of that, Amy, because we only count the green. Now we need to count the molecular 2, black. It's the same? Did I do it right? Except I missed one term. It should be divided by 2, everything. Because it's a pairwise interaction, so it needs normalized by 2, like we did before. So now we need a count 2-2 interaction and a count 2-1 interaction. So now we need to understand what is this type 2 interactor with the self. It's the same way we counted it. The chance of a black cross meeting another black cross is given by n2, 2, and 1, 1 plus n2. Right? Times W, 2, 2. Hey, yes?
That first M term, should that be M22?
Oh, right. Good call. Good call, Winfield. Good job. Thank you. It is. Because we're counting number of black cross, its nearest neighbor, times the chance of meeting another cross. This is the chance. And times W22. And then we have one last thing is counting black-white interaction. This should be 1, 1 now, right? So take your time to write it down and digest a little bit. So when we add 1, 2, 3, 4, those 4 together, that's going to be in the mixed state. What is the delta? What is H of solvent mix? Yeah.
Are your 1-2 interactions and the 2-1 interactions the same?
Yes, in this case.
Would they?
They both going to be W12.
Okay. Would you exclude 1 or just multiply it by 2?
So you don't need to multiply by 2 because we kind of already normalized it. So we just need to add them together. So these 2 terms will cancel out eventually.
So basically by doing the 1-2 interaction in green and doing the 2-1 interaction in black, you're not double counting?
No, because each time we normalize by 2.
Got it. Okay.
If we don't divide by 2, that will be double counting. Okay. Any questions so far? Amy, and then Monette, okay? Amy first.
In the interactions between 1 and, I guess, 2 and 1, the last term, why are you multiplying by, I guess, like, how did you know that the thing that is on the top of the second fraction is M11?
Oh, you mean here?
Yeah, why could that
Oh,
be
okay.
M22?
No, let me explain. Amy asked why particular this is M11, right? So remember, the second half is counting the interaction between molecular 1 and not molecular 2. So it's counting a cross versus a circle. So we need to get the chance of what this cross meeting a circle. So it has to times with the probability of finding a different color of molecular. So let's use example of you picking dinner for random student for dinner example, because we have 6 and 8. That's great. So Amy asked, so if Amy goes to a dinner, there will be the interaction with the female and male. This will be female, female. right? So it will be 2, 2 is the same. So Amy, in this case, you have to times the number of male students divided by total number. So you can times the chances of you finding a opposite.
But aren't those interactions, since it's like 1 with 2 or 2 with 1,
Yes,
same?
so this is the same, right? But the chances of finding your dinner partner is not the same. If we use the M11 divided by M11 plus N22 is not equals to N22. Does it make sense? If we use example, the chance of you going out dinner with a female student versus a male is not the same. Because N1 is not necessarily equals to N2. So let me, instead of these boring numbers, let me help you, Amy, a bit more. So let's give a detailed example to help Amy understand. So Amy, let's say how much you spend on dinner when you go out have a dinner with another girl.
Hopefully less than $40.
Okay, let's put it 40. Okay, so $40 with just this some random number. Okay, let's put $30. Guys spend. Okay, and 2 guys go out. They're really thrifty. Let's say they spend $10, 2 burgers, and they share it. Or 1 burger they share. So now we can calculate. Amy, think about in terms of when we have the class go out for food. Before we mix them, that's easy, right? But now after we mix, so what is the chances of the spending on the dinner? So let's use you as an example. So there you're gonna pick someone. So there's 6 of you, right? Each of you need times 2 because it's always gonna be 2 of you go out. So M will be equal to M of sides. Then the important part is you're gonna go out, the chances that you go out with the female students is 6 divided by 14. Okay, this matters because if you times A by 14, you are not paying $40. In this case, you're paying $40 because female interaction is 40 for dinner. So if you go the other way, you need to count 6 times 8. This has to be 8 because 8 is number of opposite color of molecule. And this is going to be interaction 30. Does it make sense? It help you understand better? Oh no?
I think so.
Okay. Because that's where the chance of you finding what the color. In this case, it's 8 by 14, or you can generalize it is going to be N22 divided by N1 plus N22. Everybody good with it? And of course, when we go out, we don't want to ignore the half of the other class. We also need to add, let's say, Joseph, I'm going to use your example. Joseph is going to pick the class girl for dinner, and again, this is going to be the same, but we now have 8 male students, and they're all going to eat burger. Sorry, guys. Right? And we have the other half. Gonna go out for this way. So that will be total opportunity for the class. We pick any 2 to go out for the dinner the total energy. We can think about this will represent the entropy of the system. And this very long equation basically the same. It tells you what is the chances of contact. So this shows what the energy of each contact, the chances of contact. C defined as chances of contact. C12 is chance of one molecular contact 2, which should be M1 divided by N1 divided by M1 plus N2. So if we put these everything together, the solubility parameter, when we add everything together, will be chance of contacting 1 minus 2 W11 plus half of Z M1 minus C12 W12. And Z is number of site, M1 is total number of number 1 sites. So if we add everything together, we will get the white colored ball, or one type of molecular contact white, plus white ball count red. So half of M1 times Z times X1 W11. X1 here is defined as M1 divided by M1 plus N2, okay? So that's the chance of you meeting the same color, or volume fraction, or molar fraction in here. And you can times the other one. So that will be exactly the same as we discussed in the classroom. W11, W12, W12, W22.
What is X?
X is mole. So it's, oh, sorry. X is the chance. So X is a molar fraction. It's M1 divided by M1 plus N2. So it's a molar fraction. It's basically the same as this one. Molar fraction. So how much mole of your molecule divided by total number of mole? Okay, so let's move forward. Let's try to summarize everything in the next 10 minutes or so. So now we discussed about in the solution state, what is the pure state. So this we have covered in the last 2-3 slides. We now can get mixing. And since there's so many 1, 1, 1, 2, I'm kind of color coded for everybody. So trust me, I didn't mess it up. When you add, these would be number of states, number of coordination, state nearest neighbor divided by 2. That's the same normalization factor. And in the bracket, there will be the mixing states minus pure states. So pure state before mixing for molecular 1 and molecular 2. And we can rearrange it a little bit because we can get W12 in one bracket. And we can get 1, 1 in one bracket and W22 in one bracket. Nothing crazy. But now, one simple thing we can do is to do a little bit simplification. So we introduce one new term. So what is N? Total number of moles. Who said that? Thank you. Okay, so that's the total number of moles. So this basically would equals to M1 times M2 divided by total number of moles. Because remember, X2 equals N2 divided by M. Okay? X2 is M2 divided by N. Same for this one. X1 here, we can simplify it because NX1 minus M1. This we can written as M1 bracket X1 minus 1. And this can be further simplified this. M1 times N2 divided by N. Same for W22. And you will see that they all share a common term as M1 times M2 divided by N. So we can pull this out. So delta H mixing will be number of moles for first molecular, number of moles for second molecular divided by total number of moles. Let's use example of 1 mole toluene, 1 mole hexane. So you would have 1 times 1 divided by M2 would be, N would be 2. Okay? So this will be 1/2 times Z is nearest neighbor times the bracket W12 pair interaction between 1 and 2 minus pair interaction of W11 and minus half of 2,2. So in the end, you can see the delta H of mixing, if it's going to be give out heat or take absorb heat, if it's going to be positive sign or negative sign, totally depends on this bracket. Amy, yes.
Is this delta H mix?
Yeah, delta H mix. So it totally depends on here. So what is this? This boils down to W12 minus half of 1 half of 2,2. So what this means, okay, now let's go through the physical meaning. So the interaction strengths after you mix minus their normalized 1, 1 and 2, 2, you can think about getting another bracket will be W11 plus W2 divided by 2. So that depends on how much pair interaction you have before compared to what you had after. That we can further simplify and introduce one of the most concept in our polymer physics is if we define this to be a new parameter called chi or Flory-Huggins parameter, we can get what is the enthalpy before and after mixing. So we introduce now a very important concept called Flory-Huggins parameter chi. So what is chi defined? Chi is defined as number of sites times delta W, and delta W is just after the pair interaction minus the pair interaction before we mix. Okay, so it's a delta W divided by KT. So the sign of the chi matches what's the magnitude of W12 and W11 normalization. So if we have a positive chi, that means W12 will be bigger than the average of those two. So we define a chi, and we will go through a lot of exercise about what this Flory-Huggins parameter. If you heard about parameter named after someone, it's probably important. That's definitely true here. It's one of the very important parameters for everybody to understand, okay? If we define this chi parameter, we now can simplify this enthalpy of mixing into delta H mix is equal to M1 times X2 times chi times KT. Any question? So this is exactly here. So M1 is still M1. We can simplify N2 divided by N to be X2. So that's where M1 times X2, where it's come from, M1 times X2. The chi replaced everything in this red circle. And since chi needs normalized by KT, so we give back a KT. So that's what enthalpy of mixing is. In the regular lattice theory, your enthalpy of mixing is proportional to M1 molecular volume fraction of X2 molecular times chi. And KT is just a constant. Boltzmann constant times temperature. Oh, very beautiful. Very simple. Elegantly written. Right? So any question? Amy, yes, please.
What is N1?
N1 is so this is a This is number. This is a mole. Number, mole. They differs by n or chi. This is a Boltzmann constant. This is called gas constant. If you use K times a mole of K, this will be equal to R. So for the simplicity of discussion, focus on the first half for you, okay?
Can you say that again? So the N is moles and M is number of molecules?
Yeah, M is number of molecules. Okay, so one last thing I want to cover today is we're reaching the end of solution theory. How exciting. We calculate entropy, we calculate enthalpy. You guys did a fantastic job. So we now can get the final question, will they mix or not for any solution molecule? It's such a beautiful theory that everybody should be proud of yourself, right? You guys can apply this. We know delta H, we know delta S. We add everything we learned from these two, we can get delta G. This is the ultimate question about will you mix or not. We need to consider the enthalpy and entropy. So I have did the job, written down the final equation for delta G for you. So it's RT times N1 log x1, N2 log x2, and N1 x2 chi. And the first part is the entropic contribution coming from the last lecture. This is entropic contribution coming from this lecture. So let's do example in the next minute. If I'm mixing toluene and hexane, 1 mole of toluene, 1 mole hexane, delta G would be RT. R is a gas constant. It's 8.314, something like that, times the temperature. So this is 300 K. You can see this is a positive, so it doesn't determine if it will mix or not. The criteria for a mix is delta G need to be negative. So it's either above 0 or below 0. So those two are both positive. It won't affect the mixing or not, but we'll make it magnitude smaller or bigger. N1 will be 1 mole times log x1. X1 is the volume fraction, molar fraction. That will be 1 divided by 2. That will be 1 times log 0.5 plus 1 times log 0.5 again, because we have equal volume mixing, times N1 is 1 times 0.5 times chi. So only thing we don't know if they will mix or not boil down to this chi parameter, right? If you want to mix, the chi need to be small so that your entropic terms is bigger than enthalpic. If chi is negative, everything definitely will mix. If chi equals 0, it may or may not mix. If chi is very large, you will not mix. So we will talk more about what this chi means, and we can discuss it in more detail for regular theory. Okay? Then the next class we will also discuss about the Flory-Hagen theory. In this case, we're only dealing with small molecular mixing. We never touched anything about polymer. We know Derek might show up and say, hey, we're a polymer department. We have to talk about polymer. So next class, we will talk about polymer. We will extend what we learned from the solution theory mixing into the polymer mixing and explain how does polymer mix. And we will also show you guys a few examples how to calculate G. I think one of the feedback is everybody wants to see a little bit more examples, so we will show a few more examples how we calculate delta G. Okay? With that, I'm going to wrap up. Any question for me? If not, let's wrap up the class and you can drop the exam here. Thank you.